We'll go up it a little bit on the way back, but that's one of the larger, it's the largest bar in Moses Coulee. So you can catch it just the edge of it here. Because we came down the road this way, and then we turned onto this road here. So the bar is it's hard to miss it. It's just so different from everything else.
Are those not also bars that we crossed on the road higher?
Yeah, absolutely.
But
they're smaller and they have a very different. They're flat on top, so what they are is really outwashed. That's been dissected and sized, right? As opposed to being like so. This bar.
That's a point bar.
It's a pendant bar, technically. So kind of like a point bar, but not so much as in point bar in the traditional point bar of a like meandering point bar and the inside of the channel. It's building out because it's sheltered behind a rock, another rock, right?
Sure, yeah.
So there's a back eddy essentially created by the flow separation.
Like a snowdrift being
That's
posited behind an
a
obstruction.
fence, yeah, on the highway, exactly. Okay, so this is Moses Coulee. We came down the coulee, and we were just chatting about the bar that we could see across the valley. We just catch a little bit of it. This line here is the road that we followed, but we turned and are headed north for a little while, and right now we're right around this area here. So that person are in the far distance over there, and those sort of rounded knobs that you see is this area here. That is the moraine as a landform, as best as we can call something a moraine inside Moses Coulee. That's it right there. It's that kind of rounded, hummocky area, but it's got lots and lots of basalt in it. So I don't even know how much of that is basalt cord and how much of that is in fact sediment, because you can see stripes of basalt on the hillsides. There's big blocks we call haystack boulders in it. So it's got a lot of basalt. Because there is basalt all the way through this area. So we've dissected a lot of you can see the basalt all over this. Great examples of columns throughout here. And right now we're standing on what would be reasonable to call a bar. In other words, it's a sedimentary deposit. It was emplaced by meltwater moving through this area. And it is in fact, there's a number of these different bars. And there's one here in particular, this one, this kind of hump, is the hump right behind us. Yeah. So that flat surface that you see with a gentle slope moving towards us is this slope here. And even from here, you can see that there are levels to it.
Benches.
Little trim lines. So all these lines speak to, think of them as levels of water, levels of erosion. So when I talk about trimming, I mean just sort of eroding a little bit. And you see these trim lines here as little steps that come down. Okay.
Terraces?
Like little teeny terraces?
Yeah, not quite, because not terrace in the traditional fluvial sense of a former floodplain that you dissect, right? So not technically terraces, but terrace-like in terms of being relatively straight. Technically, terraces have slopes. These they're very subtle slopes. These probably have slope because there would have been a slope on the water surface, but they might not be quite a slope or continuous. The biggest thing is that we're not really looking at a feature that represents a valley floor, a continuous valley fill, and the surface. Does it make sense?
It's a symbol.
It's a localized feature that we've reshaped with water. These are more akin to valley floors, or let's think of it as floodplains, except that, so if we apply like this river thinking to these areas, we quickly run out of options because it doesn't really fit those ideas. So we can talk about the concepts, but we invariably talk about the exceptions to the concept. Yeah. But think of this valley being full of sediment. And what you're seeing through there are indeed levels, different surfaces, different elevations. They're all channelized, but they represent incision, they represent erosion. So the highest surfaces have been eroded into to create this kind of irregular stair-step pattern as we go through. Tom?
So it's shaped like a pendant bar, but it's really not a pendant bar. It's really an erosional feature.
I think it's not quite. I think this feature might be pendant, but I think this is in fact an erosional remnant where the shape is partly dictated by what creates the erosion. So we're kind of like in the hair-splitting category of pendant, not pendant.
Yeah.
The best pendant example. So the idea of a pendant bar is a bar that develops in the lee of, right, so sheltered by some obstacle. So the big bar in Moses Coulee is a great example of a pendant bar because this knob of basalt if the flow is moving this way,
Right.
shelters the area immediately downflow of it. So there's a low pressure and low velocity area. In fact, there probably would have been like a bit of a backheading into this area. So we allow sediment to be trapped there because the water moving through here is moving very quickly, and that area expanding and back-eddying is slower, and so we induce deposition of sediment. Pendant to this, so we require the obstacle to create the conditions for slower flow that then allow for deposition in that zone. We're good with that? So it's pendant in relation to that obstacle. At the end of the day, at the end of Moses Coulee, there's another big bar that we call an expansion bar. Flow comes out of a constriction, the coulee, into the Columbia where the flow expands, and we initiate and induce deposition because the flow widens very rapidly, and so we deposit most of the sediment. So there's different flavors of bars.
I'd call that a delta then.
Only I'm going to be the asshole today. Like technically speaking, actually, well,
etc.
It's not a delta because it's not going into a pond of water?
correct.
Gotcha.
It's going into a pond, but the pond is so temporary,
Yep.
and the delta is so not driven by a river in the traditional sense, and its architecture is also probably quite different from the typical delta. So if you were able to image, the stuff, you realize there's some aspects that are kind of delta-like, but it's not truly a delta in the traditional sense of a delta for really coarse sediment like that. So you'd see foresets because there's a bunch of migrating bed forms, but it's not the foresets of a delta.
Okay, you thought we weren't listening, but you said the esker terminates in the series of deltas.
Yes, those are deltas. Okay, so not a traditional.
But I'm the asshole.
You're right. You're right that it's more delta-like in that sense, and that it comes out of a conduit, but it's not a river. You're right. So that's
They're both coming out of conduits. Okay.
yeah, both coming out of conduits. The eskers and the deltas that on the Waterville are nowhere near as energetic,
Right?
and they are coming into a ponded area of water. So we could split hairs about the use of the term delta, but I probably bet dollars to donuts that architecture of those is more delta-like than the architecture of the bar itself at Moses Coulee. But you're right; it's not.
You
It
look at
doesn't,
the
doesn't
field work
fit
to
the
know
story
that.
perfectly.
I haven't seen the field work. Okay, cool.
Okay, that's it. We're done. Let's go. More questions like that, we're out of here. Okay, just kidding. So, a couple of things. We're here because of the so-called Moses Coulee enigma. The enigma of Moses Coulee is the fact that, and Saber was on that at the last stop, when you look at the coulees, like Grand Coulee, the other one that we were just in before, we talked about the breach. Whenever that breach happened, at some point it connected enough to the Columbia to divert flow from Lake Columbia. You drive into Moses Coulee, the second largest coulee in all the Scablands after the Grand Coulee. And if you follow Moses Coulee and say, oh, there must be, if it's so big, there must have been a lot of water moving through here. Where does it connect to the Columbia River or Lake Columbia? Because most or all the water should come out of Lake Missoula, and therefore there should be this connection to the water source that allow it to convey that Lake Columbia water. So we're near the head of Moses Coulee, so we're now here on this DM. And if we drove this road a bit further and up this little canyon, we would go to a place called Jameson Lake, and you go past Jameson Lake, and then you would go up a slope and you drive onto what we call the Waterville Plateau. Mm-hmm. You're firmly under the footprint of the Okanagan Lobe. You're near the town of Mansfield, and the coulee disappears. There is the continuity of the coulee changes basically around this corner, gets narrower, not as in size, but then the coulee disappears entirely. And the enigma of Moses Coulee is, how do you get a coulee this big if there's no connection to the pathways for water from Lake Columbia? Does that make sense for everybody? We don't have that problem here because we got a big coulee, but we got a big opening, a big siphon that allows any water from Lake Columbia to go into Grand Coulee. So there are different ways around dealing with that conundrum or that difficulty. I might do something. We might try to raise this so we can see it better. Can you see that middle diagram enough? Okay, so there's three scenarios to get water into Moses Coulee. I'm going to walk you through the first two, and then I'll tell you about the third one, but most of you know my poker hand, and so we'll tell you about the third scenario after. Scenario 1 argues that we block the Columbia River. We need to divert Lake Columbia water into what we call the box section of the Columbia. The box section of the Columbia is the reach of the Columbia between the Grand Coulee Dam.
Sorry.
Oh, that Hexeth, he always comes through.
Oh boy.
Ooh. There you go.
Must be too suspicious.
The Canadian was not drawing penises in the sky this time.
Okay. So the idea, this first idea, is that we're going to get water from Lake Columbia before Okanagan Lobe has blocked the Grand Coulee, and before Okanagan Lobe has crossed the Columbia fully to block off this pathway. The moment that the ice comes across, then that pathway is blocked. It's no longer in play because we basically blocked it here, and so this segment is under ice of the Columbia. Brewster and Bridgeport over on this side, Grand Coulee Dam's over on this side. So early, and this time we'll talk about dates after, we block a portion. Selectively, we have to block this portion of the Columbia River, the Okanagan Lobe, coming down Okanagan Valley here. But we need to leave this part open so that Lake Columbia water can encroach into here, but get stopped here by early Okanagan Lobe advance. Everybody's with me so far? Does that make sense? So we're selectively damming the Columbia here, but not there because we need that pathway open. If we do that, the idea is that this acts as a blockage and it backs the lake, Lake Columbia, it backs it up this area called Foster Creek today.
What was that for, Foster?
That's Foster Creek. There's another one that's confusing. It's called Foster Coulee on the other side. But this is Foster Creek. Block the Lake Columbia, back up the water, raise the water level up to this part of Foster Creek, and then overspill water out of Foster Creek into a series of channels that were mapped by a guy named Larry Hansen in the 1970s. Larry Hansen was one of the first persons other than Brett's to work on the Waterville Plateau and Aaron Waters in those days in the 20s. But in the 70s, he wrote his PhD thesis here. And he mapped some of these channels here that I've highlighted here and a few of these, and he called these the Mansfield channels. Larry Hansen's maps is sort of limited to the most obvious channels that exist that we can map. And the idea, in fact, this idea was sort of reutilized, repurposed by Richard Waite, who argues that you back up the water and you spill it over here and connect it to the Mansfield channels. Joel Gombiner and I have since done some mapping, and what you realize, and this is what you see on this map, and even beyond it, but we're not showing all of those channels. Similar channels occur up here as well. Larry Hansen's Mansfield channels are actually part of a bigger network of channels, similar style of channel, eroded into till, down into bedrock, but a much broader and much more extensive network of channels. So Larry Hansen mapped a segment of it. The more obvious one, he did this without DEMs, did this with air photos and field work on the ground. But this idea, and I've got both scenarios on here. So this is called scenario 1. We need the ice blocking the Columbia here, right? We're good with that. So otherwise it would go around this bend and drain south to Wenatchee. So we block it here, but we don't block it there. We back up the water, we back flood Foster Creek, and we overspill at a couple of critical elevations. 680 meter above sea level is the lowest elevation, the gap, and we get the water moving there, and we funnel it into Moses Coulee. This is the first idea. It requires some selective blockage, and it requires that so let's talk elevation. There is till. We can map till, so we can be sure that the ice moves over this area. and that till is roughly at about 300 meters above sea level, which means that we need to have ice that is going to be at least 340 meters thick to allow the water to pond to that elevation and overspill. We're good with that idea? So we need a blockage. We need to raise the water surface to a minimum elevation that needs to match the overspill elevation through here. Okay? So what we need here is a roughly 380 to 400 meters of ice on top of the valley floor to allow the water to rise enough to overspill. Saber.
Well, when you're talking about overspill, I would assume for this level of carnage,
Yeah.
you need like 100 feet, 200 feet or more of overspill. So the ice would have to be even higher than that to cover that level of water overfill?
100%. This
Okay.
is the minimum. This is the minimum. This is just what gets the water over the lip of the bathtub. You want a big amount of water, you need a lot, you need more.
Right.
Okay? There's another issue. We'll pick on Gary a little bit. The squirrel with the acorn and the wall of ice. This is not a wall of ice. In other words, when you're here, the elevation of the ice surface is 0, just on the other side of the ice, and then it starts to rise. So even though we say, hey, ice margin here, no. Ice thickness, 380 meters. Where's the ice margin when the ice thickness is 380 here? It's got to be somewhere else. That makes sense for everybody? Like you don't go from 0 ice to 380 meters thick ice like a wall of ice. It's not a wall, it's a sloping surface. So where's the ice margin? Well, you can sort that, you can figure that out with the estimates. So if you think about the gradient on a glacier, there's a range of values you can use, but basically most modern glaciers that are outlet, we consider outlet glaciers, we did these calculations with a range of different possibilities. But you end up with slopes of about 2%. That's about ice surface slope. Right at the front, it's a little steeper, but beyond that, after the kilometer, it flattens significantly. Sometimes they're a bit steeper, 3%. If you put a 3% slope on the ice to have 340 meters of ice here, and you just project that at that gradient of 3%, you have your ice margin, depending on the gradient you put on the ice, 15 to 80 kilometers south of this location. Now 80 kilometers gets us past the Withrow moraine, so that's out, okay, because we know that the ice stopped here, didn't go any further, but it's less than that amount. If you get the ice margin, so if you project and it goes further than about 12 kilometers, the ice is in Foster Creek now, and the ice is blocking access to Foster Creek for water. Are you following what I'm saying here? So you want 380 meters here, but to get 380 meters here, the ice margin has to be at least 14 kilometers south of this location. And 14 kilometers south of this location means that ice has moved in here and has blocked access to Foster Creek. So you can't even get the water into Foster Creek, let alone rise it enough to overspill. That makes sense for everybody? Yeah. So that's not great.
What would happen if it was if it's not 308, if the ice margin is there, but it's not at the line one, but it's not 380 feet.
Yeah.
What happens to the Columbia? Is it still blocked?
So if you've got the ice margin here, and the margin really is, that's a great question, Jennifer. If it's right here, and you get a sudden influx of water coming out of Missoula into Lake Columbia, and there's no blockage from the other side of Okanagan Lobe, so this is open, and the ice margin is here, it's probably rising so fast that it's floating the ice margin, detaching it, going underneath it or over it, and it says, thank you very much, I'll keep going. It rounds the bend, and there's no blockage going on.
Okay, and doesn't really get blocked.
It doesn't get blocked at all. It's too thin.
Where it is.
You got it. Does that work? So this is the real issue here, is that if you need it at least that thick,
in that spot,
then there's some limitations as to how efficiently you can in fact not block the entrance to this, which is critical because you gotta get the water through here. Okay, so that's one scenario.
And since you're talking about hundreds of feet of water to make this happen, you need an even higher margin there, which
these are all minimum numbers, right?
The higher you make that, the more you block.
The harder it is.
Right.
You got it. The thicker this needs to be, and we can play around. Okay, so flotation thickness for the ice. If you can make some assumptions about how much sediment is in there because that holds it down a bit further. Those numbers don't change radically. We did the calculation with a percentage of sediment in the ice, so we kind of try to account for that. The other thing is, if you look at this map, ice comes down the Okanagan, follows one side of the valley here. This is an area that we call the Omak Plateau, and then there's Omak Lake here, another side. And so that ice comes down the valley, kind of splits around here, covers this surface because there's eskers and till and everything, every clue of glaciation. So this requires that we don't block here early. So the same problem that arises here, and it's requiring that we don't block the Columbia upstream, right? Which could also happen. But let's just go with that. If that's the case, maybe that might be reasonable enough because we might be getting a bit of cascade ice from the west spilling eastward and then build this up a bit. But the thickness becomes a real issue to getting water high enough to overspill into here. Scenario 2 says, okay, we're going to get water into Moses Coulee by diverting it along the margin of the ice. So we're going to advance the lobe. So this is where the ice margin needs to be, ice margin for scenario number 2. And we're going to do that by, back to the conundrum of the Grand Coulee scenario, we need the Grand Coulee closed, unbreached for this to work. And we need to have it unbreached probably as far as Steamboat-ish area. Because there is a gap called Foster Coulee, not Foster Creek, but Foster Coulee, that allows, if we get water moving through here, diverting, to pass into this area and enter essentially in front of the ice and shunt it into some of these channels towards Moses Coulee. So there's a lot of circumstances that have to come together for this to work. This has to be full of rock, not ice. Can't be open. If it's open, this game over. It doesn't work. The siphon is open, the water goes through. You're not getting the water high enough to spill over here. So this requires closure enough here to move through this way.
So was Moses Coulee before or after the last Grand Coulee?
Before. We'll look at the dates in a second. So if it's open, both these scenarios don't work. But if this is closed, let's go along with the idea. If it's closed, then the idea says we'll divert water through here, pass it through Foster Coulee, and then shunt it along the margin into some of these channels, and then lead it into Moses Coulee, which is coming down in this area. The challenge, of course, is Moses Coulee is widely recognized as having had discharges that are mega flood in scale, so 1 million cubic meters per second, or maybe a little shy of, but very substantial discharges. And if you're moving that much water, there should be a really prominent channel, some way of conveying that water into the coulee. There should be a pathway. Every other place that's got big discharges has some channel evidence of that discharge moving through. And we don't have it. We don't have like an oblique northeast southwest directed channel system that feeds into Moses Coulee for this diversion. Now, of course, if there was water passing through here, we'd expect a channel here, but the argument would have to go that we've since removed the evidence of it when we breached the Grand Coulee. So that's gone, but we'd expect something to connect.
How about a river on top of the ice?
Yeah.
River on top of the ice or river under the ice? So when you look at the map channels that we interpret as being subglacial channels, even that network has nothing that resembles an oblique northeast-southwest conduit. It's radial. In fact, it follows pretty much the shape of the ice and the gradient of the ice. So if you think of the lobe, the Okanagan lobe as being thick to the north and thinning to the south along the margin, the channels are just equally as radial as the ice surface itself. And so part of this is part of the reason, or the arguments that we use to make the case that these are in fact subglacial channels. There's more reasons to that, including the eskers and the recessional moraines that overprint those channels, so the channels have to come first. But for us, that is a much simpler explanation, is that in fact Moses Coulee is getting water from a subglacial drainage network. It doesn't get water from Missoula, and perhaps never, ever did it get water from Missoula. Sorry?
Apostasy.
Because even if you try to make these work, you still have to explain why there's this channel network here, right? When does this form and how does this form? The most obvious convincing channel network is not an oblique one, it's this radial one with all these eskers and recessional moraines in it and so forth. So this for us is a bit of a resolution to the enigma of Moses Coulee. It's not so much as once you sort of integrate the subglacial hydrology, then you've got a mechanism to create large discharges into Moses Coulee, and it allows us also to connect more of the subglacial and kind of like near margin topography. So we're back to Tom's comments or questions about these types of channels. So back to where we're located right now, this is Moses Coulee going to Jameson Lake, and in fact this is Jameson Lake through here. And the part that you're looking at here is really, it's this section of channels. So there's a number of major, very large subglacial channels that connect to this zone. And so it's this one, and the coulee itself, and a few of these that divert and pull into Moses Coulee. So we're going to dissect very strongly through here, and we're subsequently going to deposit sediment either on the waning stage of some of those subglacial floods, which at this point might be just emerging in front of the ice, where they could be sort of like on the cusp of being subglacial or proglacial in front of the ice, but the water itself is being delivered from beneath the ice. And then during deglaciation, when we start to make all of these recessional moraines, you all predicted there should be some water also being generated, and yes, there was. We're going to reutilize some of these channels to evacuate some of that meltwater as it goes through.
Arguments are dependent on current day elevations.
Yeah.
Big thicknesses of ice have depressed the crust, and there's been rebound.
Yeah.
Is it enough to screw up your story?
For us, not really. It's more of an issue for other scenarios, particularly the overspill one, because if you think of the distribution of ice thickness in this, it's thicker to the north, and so there would have been
It goes down.
exactly the weight would have been greater to the north, so the depression would have been greater. And typically, ice sheets have a bit of a we call a forebulge in front of the ice, so there's like a depression under the ice, and then there's a bulge in front of the ice that kind of raises the surface a bit, and then it drops again back to the unaffected landscape, and this forebulge migrates. So in front of the ice or close to the margin, there's an extra high thing to get over, which is the forebulge. And that extra high thing is problematic because we need to spill water over that lip, right? So if with the forebulge, that lip is potentially even a bit greater.
Makes it even harder.
In fairness, the forebulge extends for kilometers often, so it's a very subtle rise, but it doesn't help. It doesn't help these scenarios in any way that you think about the argument.
Like the floor bulge in front of the thrust
Yeah,
front in
yeah.
Alberta.
Yeah. So,
And going back to the Model 1 going through Foster Creek,
yes,
shouldn't you also expect some kind of channeling from the overtop?
totally.
And we just don't see it.
No, there's a breach there. There's a bit of a gap, but is it big enough?
So Jerome, one thing I'm not clear about, right? Like, like if we go with that theory, like normally, like we've said that all these coulees are formed due to headwater erosion, right? Like the erosion started from over there and it backed up
Yeah.
till here, right? But so there must be enough water going all the way over there to have started the, the basalt columns or whatever to be eroded and then come back. But would that channel network to give us that much amount of water to do that?
Yeah, so we did some estimates of how much water you can move through this network. And so again, you come up with their estimates, they're kind of first order estimates, and you run through different scenarios. So we did it with, let's just back it up a step. There are many different ways you can estimate discharge. We took one that's relatively simple, where you just say, okay, I need to know how fast the flow is moving, and I need to know the cross-sectional area of the channel. So the cross-sectional area of the channel we can figure out because we can just measure the dimensions on the map. So we took a number of cross-sections. We said, okay, imagine that they're all conveying water. So we ran different discharge scenarios. If 100% of the network is moving water, or if 50%, right? Because what we don't know is if all the channels are operating simultaneously. or maybe there was an area that was operating at one time and then it shifted elsewhere. So we ran scenarios with 100% channels operating. Everything blue is moving water, 50%, 25%. We just come up with different ranges. We're estimating the velocity based on the size of boulders that are in the channel. So those that are reasonably moved, there's a threshold velocity you need to move those boulders. So we come up with a discharge calculation. And we run, the range goes from basically 10 to the 6, so a mega flood scale discharge if everything is operating, to if only I think 20% of the channel is operating, 10 to the 5, 10 to the 4. So there's a whole range there as a function of, but it's in the ballpark. It's in the ballpark of the discharges estimated from Moses Coulee by other means and other people.
Jerome?
Tom, yeah, or there's,
When the subglacial channel is flowing, crosses the Columbia River Valley,
yes,
what enables it to climb back up onto the Waterville Plateau?
okay, good question. Hydraulic pressure in a nutshell. But so when it crosses the Columbia, if you ever boat down the box section of the Columbia, what you see is that there's a pile of very fine-grained sediment in that reach of the Columbia. Lacustrine-ish in appearance, very fine silts, fine sands, a bit of clay. And then it's capped by till. So the till is not right on the bedrock as we might expect and as we see in many other places on the Waterville Plateau. It's at the top of these lacustrine sediments. These lacustrine sediments, probably the simplest explanation is they are filling the Columbia as the ice is advancing. It's outwash. It's outwash in front of the Okanagan lobe as it's moving south early on as it's advancing towards its terminal position, but hasn't gotten there yet. And it's delivering meltwater, which glaciers do constantly, and it's mobilizing whatever's on the landscape. And why so much silt? Largely because these areas were out of the Columbia River basalts. The Columbia River basalts are actually, if you see this kind of scabby surface here, that's Columbia River basalt. That sort of more jointed pattern, this is the Okanagan Dome, metamorphic rocks, the Eocene stuff, takes us back and Shuswap, all that good stuff, right? Those granitic rocks weather by hydrolysis and release lots and lots of fines. Richard Foster Flint called these a Nespelem silt. There's a whole region north of the Columbia that is loaded with very fine material. It's a byproduct of the weathering of the granitic rocks. And if you actually drive, say, from the Okanagan into the Sandpoil Arm, or if you drive into the valley, the next one over that goes to Republic, you cross these little summits, and the summits are loaded with rounded boulders of granite. And they're not rounded because they were flood boulders. They're rounded chemically from deep chemical weathering. So in interglacial periods, there's active chemical weathering on these granitic summits. We weather the exposed rocks. We release lots and lots of silt. It washes down into the lowlands. Okanagan lobe comes in. Thank you very much. Piece of cake to mobilize. It's so fine. And it flushes a lot of that fine material into the Columbia. So it's basically going to pave its own driveway to get across the Columbia. And then the till that caps that tells us that the ice moved over it. So your first question is, how does it get over? It gets over relatively easily because it's nowhere near as deep as it is today. And we can actually see that surface quite well. And it's roughly filling close to 100 meters in places of material. After that, to get over it, hydraulic pressure from the water. So sources of water north of here, on top of the ice, under the ice, there's a hydraulic gradient that allows that water to have enormous potential to overcome adverse slopes. It can go uphill. There's, you could argue in some places around, where are we at here? There's some erosional patterns through here that are pretty consistent with what we see when flows encounter what we call an adverse step, like flows encountering a positive step like this and they have to go over it. They tend to block and create a bit of a vortex this way, but then they shed vortices that go over the lip and they become super straight, super thin, and super fast. And if you look at that, there's a whole bunch of streaks in the basalt, erosional streaks with little potholes that, to my mind, kind of look enough the part to think about water moving over that bedrock lip as it's under pressure to move through this area. Not everybody would agree with that, but so there's ways. I think it's not this is not the biggest obstacle to get water. But there's a lot of gradient from depending on. So this brings another good question: is where's that water coming from and how much of it? If we're going to argue that it can be close to mega flood discharges, What's that?
Canadian water.
Yeah, so there's evidence for big lakes in the Okanagan during deglaciation, but also before. Okanagan Lake itself was a much larger lake, glacial lake, and it's the perfect scenario to trap water, like these big mountain valleys under the ice. So it's not that difficult to do.
So when we were driving,
Yeah.
down from that last stop, and so there's that row of big erratic.
Yes,
They were basaltic.
basalt. Yeah.
So there doesn't seem to be a big enough flow to have broken up Columbia River basalt
Okay.
across the Waterville Plateau. So
Okay.
where did those come from?
Good question. So, so what you saw, what we see is what we commonly on the Waterville. There's even more though than the Waterville Plateau. They're called haystack boulders. They're often thought to be a product of ice ripping up big chunks of basalt.
So it's ice ripping up.
Yeah, except that you can go beyond, like you can go to the Afraid of Fan and you're going to find a giant boulder that looks like a haystack boulder. So we call it a haystack only because we're north of the ice margin or close to the ice margin, but otherwise they look the same. And why couldn't they be hydraulically plucked, which you can do? But let's go with the ice story, which is fine.
Okay.
So as the ice encounters this area, when we argue that there's meltwater being released, this is not like 24/7 all the time during glaciation. These are probably episodic events. And between those events, which could be hundreds to thousands of years between them, the ice is on the bed and it's still advancing, it's still moving, it's still eroding. So we're not suggesting that the ice never touched the surface. It's very clear. There's drumlins and all kinds of other evidence of erosion. That ice was firmly in contact with the bed. It just goes through periods where it's detached, especially around the conduits when the pressure is enough that you lift the ice a bit. And so you detach it. So in those other times, the ice is in fact firmly grounded on its bed and is capable of quarrying big bedrock. And when you encounter, like to Tom's question, when you encounter this lip, that would be a good place where you could start quarrying big chunks of basalt, especially big chunks of entablature, not the columns, which is what most haystack boulders are made of, that the smaller kind of crinkly portions that are the entablature. The other part is if you drive the Waterville, there's a few key spots, Beasley Hills and a few others, where there's big chunks of basalt that have been dislocated from, so they're kind of these random big blocks of basalt. They're not individual haystack boulders, there's big blocks of boulders. And those are probably what we call glaciotectonically detached. So the ice can either attach itself so firmly to the bedrock that it kind of couples itself and rips it out of place. A good way to do that, incidentally, is, and we see this happen with modern glaciers, if you pass water under the ice very quickly, like I was suggesting, you erode the bedrock, but you also erode the base of the ice. You generate water in the process, so you sort of add water to your system, but you eat up the ice, and you eat up the sediment. And what you end up doing after the water is passed is you've removed a substantial thickness of ice, and the ice that remains is actually quite cold. So if you think of the temperature profile in a glacier, it's coldest at the surface because it's in contact with the cold air, but at the bed, it's near what we call pressure melting. It's basically 0 degrees. It's liquid water at the bed. And if you erode quickly with a flow of water, the base of the ice that's warm, you end up with sub-zero, sub-freezing temperature ice, and then you plunk it back on the bed and it freezes itself to the bedrock, and as it keeps moving, that coupling didn't exist the same way before, but now it's kind of like thermally coupled to the bedrock, and it can that's one of the ways you can dislocate big chunks of rock from the ice.
Wouldn't that like grind it down as it travels under the ice?
After the fact, yeah, and so you do see that those big blocks, they're sometimes, a kilometer long. They're big chunks that are eroded after the fact.
But that ice above the water is also going to put pressure on the water.
Yeah, to drive it.
I know you want Canadian content here. I think you've opened yourself up to another idea.
Yeah.
If this is the case with the edge of the ice,
Yeah.
and you want to bring the water from Kelowna and
Yeah.
Vernon and the Suyus, wouldn't it be easier to be floating the ice a little bit and to be bringing it from Lake Columbia around that way?
Floating
Thinner ice here,
into the ice.
thicker ice there, easier
Yeah.
to get the water under the ice and down
Oh,
that
I
way.
see. Okay, maybe. Yeah. Except that if you do that, Gary, the pressurized subglacial water will go to Lake Columbia, not Columbia going to it. So this is basically like lifting the, if you lift the ice, you depressurize, right?
Sure.
And so that water that's under pressure would squirt out to Lake Columbia rather than let Lake Columbia encroach. Does that make sense?
You still got
The door's
outlets
open.
To the east. You still have the other outlets to the east. If you're getting the water
This one
up
here.
high, float that up.
Yeah.
It's going to go out those other outlets to the east.
It will go down to Columbia.
Yeah.
Yeah.
But then I read that like both Moses Mountain and Mount Bonaparte had been overtopped by the glacier. They're like
Yeah.
7,000 feet. So
Yeah.
is that like that's the elevation of the Okanagan lobe? At the center was probably higher than that, right? I mean,
Yeah.
this is massive, isn't it?
Okanagan lobe. So, yeah. So let's back it up a few more steps since we're talking about the ice sheet itself. Okanagan lobe is the terminus of an enormous conveyor that starts arguably in the Coast Mountains of British Columbia. And so in the Coast Mountains, so the simple depiction of the Cordilleran ice sheet is you got the Rocky Mountains. To the east, you got ice building up in the Rocky Mountains, you got ice building up in the Coast Mountains, and each one is sending ice to its periphery. So there's ice moving to Calgary and there's ice moving into the Strait of Georgia towards Vancouver Island, but it's also sending ice towards the interior of the province, and it's collecting in the low plateau, mid-height plateaus lower than the Coast Mountains, and it's kind of coalescing there, and then eventually it starts to make its way south. So by the time it gets to here, it's been accumulating, for millennia,
Whole
500-600 kilometers before.
Yeah.
Up north. So there's a large area of supply for the ice, and the thickness of ice, especially in this region, is a little confounding because the Cascades are also loading up with ice, and some of the Cascades may or may not be contributing ice into the Okanagan as well. Once you get to the east side, the further you move east, the more removed you are from the source of ice. And this is one of the questions that came up in the A to Z series on the Ice Age floods was why isn't this Columbia lobe and the ice around Spokane extending onto the basalt plateau? One of the arguments, or the things to consider, was that area is so far from the two respective sources of ice that it might not actually be supplied with that much. Maybe not as much as Okanagan lobe would have been. So Bonaparte Mountain, kind of on the divide onto the Sandpoil on the other side. Yeah, I think it was Ralph. It's Ralph Dawes. Thank you. That makes the argument that it's been glaciated. That's highly possible. Doesn't have to be super thick. We don't always know the thickness of the ice, but yeah, ice. Those summits were covered in large part, but not all. Because if they were, then we probably wouldn't preserve as much of those deeply weathered, relatively easy to erode big boulders of granite. So those areas, when you drive those areas, and they're very close to the margin down here, they look unglaciated. You can't find striations. You got big accumulations of really easily mobilized, the grus, the saprolite. Mm-hmm. It's all there. And that stuff is like, you could blow it away almost. But if you're a glacier, you're just going to strip that stuff away. So oftentimes, non-glaciated areas are kind of identified on the preservation of these weathered profiles that are easy to erode, and they're preserved, so they weren't necessarily glaciated. It doesn't invalidate Ralph's idea that Bonaparte Mountain's covered, but yeah, there's a lot of ice. There's a lot of ice, and it can be quite thick. And there's a big difference in ice thickness between the valleys and the summits as well. You could have kilometers of ice in the valleys, and you could have only a few hundred meters on the summits.
And then the other thing is, isn't the Cascade glaciation pretty much over by the time the Okanagan lobe's here? I mean, because like at least on the west side, the Cascades are free of ice, and the Cascade river valleys that flow to the west toward the Puget Lobe are free of ice and are flowing water down to the glacier.
Yes. So this is another wrinkle to try to make sense of all this is the timing. And the timing is tricky because even though we think of the Cordilleran ice sheet, the Okanagan lobe, as like one big monolithic chunk of ice, it's very clear that the lobes are very out of step. They operate differently. So they're fed by the same general ice area, but they each have their own little dynamic. The Puget Lobe in particular is moving over ocean water and fills basins that will, so there's a dynamic to the Puget Lobe that is, because it's almost not quite tidewater, but it's on very slippery surfaces that are very wet just because of the connection to the ocean and the Puget Sound. So Okanagan lobe is operating a little differently than Puget. We can't just say, oh, Puget moved here by that point. We should expect Okanagan lobe to be at the same place. Different different distribution, different topography, different local dynamics to the ice that allows that to happen. So I have to write these dates down because I can't remember, and they change all the time because the dating improved. But let me give you some numbers to put things into perspective as to when that is. So Okanagan Lobe gets to the Withrow Moraine, gets to here basically 15.4 thousand, so 15,400 years ago, roughly. It hits the moraine. These are all cosmogenic dates. There's some error range for every date that you generate, no matter the method, there's error range. But there's also kind of a bit of spread. So numbers 15.4, there's a few boulders that were dated that are around 17. But around that time, so the lobe gets here to the moraine by 15,000, which means that it dams the Columbia earlier than that, right? So it has to move over. And so any scenario of floods that require this diversion has to happen before, well before we get the ice over here. In fact, this requires the ice not to be there for this to work. But the scenario 2 requires the ice to be on its way and closer to the margin so we can divert water along the edge. Okay, so they all require different positions of the ice, but those are not constrained by anything other than the requirement to divert water, right? It's not like as we said, there's no major channel that says, yep, there's your channel, the ice has to be here. So 15.4. We also have a pretty good handle on the fact that there was probably 4, maybe 5 big floods down Moses Coulee. And there's some dates that come out of boulders and also other deposits at the mouth of Moses Coulee will be later today. So there's about 4 big floods that come through here. So this scenario or any of the scenarios of water into Moses Coulee happen a few times. 4 times where it's significant. In other words, 4 times where the discharges are probably on the range of 10 to the 5 to 10 to the 6, something like that. Were there other amounts of water moving through the coulee? Yeah, most likely. Whenever you melted the Okanagan Lobe, where's my line? If you look, this colored line is the topographic divide. In other words, once the ice is retreated, anything on that side of the line drains this way. And anything on this side of the line drains this way. So you can imagine how, if you're not in one of these channels, you can pond water uphill. There's a bit of a rise here that you have to overcome. And the height of that rise, the elevation of that rise is on the color code here. So you're looking often 25 to 50, sometimes a bit close to 100 meters that you have to overcome to that divide. That's relatively, it's much simpler to do that with subglacial pressurized water than to do it, or you can't do it with a subaerial drainage system. Right. You can't overcome the topography. So the floods in Moses Coulee on the bar, 17,000, 15,000. So it's close to the time when the Okanagan Lobe tags the Withrow Moraine. And in the history of flooding in the Scablands, there were early floods. So what we usually consider pre-18,000 year floods, before Okanagan Lobe had moved here. In those cases, you would drain Missoula into Columbia, and Columbia straight down the Columbia and into that big north-south stretch of the Columbia past Wenatchee. Those were considered to be big floods because they built big bars, including Pangbourne. Pangbourne Bar, one of the biggest in all the Scabland network, is a relatively old bar in that story. 15, maybe 17, depending. We built the Moses Coulee Bar, and that Moses Coulee Bar is widely thought to be kind of a blockage. It's going to dam the Columbia. We just fill it with sediment, and it's going to fill it and block the Columbia for a while. But it doesn't really matter in terms of other floods, because by that point, because the ice is here, that pathway is shut off. So we can't move water out of Lake Columbia through the Box Canyon Reach because the ice is occupying that space. So what would we have? Probably outwash from Okanagan Lobe down the Columbia towards Wenatchee.
Yeah.
But that valley, who knows what it looked like, because Moses Bar would have filled part of it, and there's a glacier at Chelan as well.
Wenatchee and Entiat rivers would still be flowing that way,
but
not
perhaps less so because it's glacial. It's cold, right? The times are cold, and so there's lots happening in the Columbia, but it's not floods. So we do the floods at 18. We shut off the valve with the Okanagan Lobe, and then every other flood that has to happen is either through Moses Coulee or eventually through Grant Coulee, or when we back up Lake Columbia enough, as we were talking before, through Telford, Crab Creek, and Cheney Palouse, when we raise it above that 715-ish meter level. So other dates for us. The retreat of Okanagan Lobe. It gets to the Withrow Moraine around 15.6. Around 14,004, 14,002, it hasn't cleared the Columbia yet. It's on its way. So it's going to move back in about 1,000 years. Maybe a bit more depending on some of the range on the dates. And then after it's retreated back from the Columbia, then this is open again. And when this is open again, then there is no mechanism or no reason to send water down the Grand Coulee anymore. And there's no reason or other reason to send water down Moses Coulee anymore. Does that make sense for everyone? And this is subglacial diversion, whatever. You can't get the water high enough to divert. You can't dam the water here to allow it to backflood to divert. And there's no more ice here to melt on the Waterville Plateau to go into Moses Coulee. So the story Moses Coulee in terms of floods is over by that point because we've reopened the conduit. And there are some floods. There are some late glacial floods that come through the Columbia after around 13,000 that go down the Columbia, but they'll be smaller. And we'll see the evidence of those when we're on the Moses Coulee Bar later and when we go to West Bar. So those are impressive features, but in the grand scheme of floods, they're actually late. So they're young features, and they're proportionately small floods, surprisingly. Despite the fact that the West Bar is just so big, it's a late, small flood.
I know some places in the channeled scablands there are evidence of glacial till over 100,000 years ago. Is there anything like that in Moses Coulee?
Not that I know of, no.
Okay.
And the only place where you'd have till in Moses Coulee should be from here on and north, right? That makes sense.
Yeah. Well, I should have said flood deposits, but
older flood deposits.
right.
No, not
Okay.
clearly, at least not identified yet. But it could, there is down here. There's a 300 feet of gravel to the bottom, to the bedrock, right? This valley floor is not the bedrock floor. There's a lot of sediment, and could there be earlier things? I mean, this raises the question of what was Moses Coulee before any floods came through, and when that was. So did we carve Moses Coulee during MIS2, the late Wisconsin times? Or has it been utilized multiple times during multiple glaciations? Brett's had that idea. Brett's basically saw Moses Coulee in the air, the terminal zone of the Withrow Moraine, and he said, oh, okay, ice margin, conduit coming out of the ice, that's my mechanism. And then he said, oh, but the coulee, so here's the moraine, the coulee extends a bit further, and Brett was totally onto this two glaciation story, right? He had that model, and he had that, we'll talk about it later, but he had that model for the Ephrata fan, he's got the model down into Moses Coulee for 2 episodes, 2 different glaciations for erosion. He places, his early map, plays some moraine, the Spokane, right? The Spokane ice sheet, Spokane age moraine, he places it right where Moses Coulee stops. There's not a lick of evidence for a moraine there, but it's a logical, like in his thought, it's like, yeah, I mean, if that's what the story is, this is just another feature.
Well, that's
and
what
it
the
should be there.
glaciers did in the Midwest where he was trained.
Yeah.
And he
Totally.
probably was looking for them because he wants to see what he saw back there.
Yeah. And exactly the same approach was taken, if you remember the A to Z series, around Cheney.
Yeah.
It was like, oh, there's these channels, and there should be a moraine, so I'm going to put my margin there. The key thing is the dashed line, right? It's a dashed line, as in it's inferred to be there, and the inference is reasonable based on what he's imagining to be happening. But he was really heavy into this two-stage, two-glaciation story of the erosion.
So the topographic